Okay, we're coming together. We've just quantified entropy, and last chapter we've previously quantified enthalpy. We're going to bring them together for those to determine quantitatively if we'll get a spontaneous reaction. We kind of did it qualitatively earlier, but let's do it with actual numbers and say, hey, this will win out. Okay, so let's remember that there's two drives here. So there's the enthalpic drive and the entropic drive. Enthalpy wants the energy in the system to decrease. Okay, so it wants a negative joules per mole or kilojoules per mole. Okay, and entropy wants to increase, so it wants to get greater than 0 joules per mole per Kelvin. So I like to imagine them kind of not battling against each other, but sometimes they can work together and sometimes they can work against each other. And I'm going to use this seesaw model, okay? So here's my seesaw. There's the fulcrum. I've got enthalpy on this side, entropy on this side, okay? And underneath, if it hits the ground on this side, the reaction's going to be non-spontaneous. The reaction will not happen. And if it hits the ground on this side, it's going to be spontaneous. The reaction will happen. Okay, let's see what happens. Okay, a little bit more detail. So, let's deal with entropy first on this side. If entropy is positive, it's increasing in disorder. It's wanting to go down. There's my positive side here. And it's wanting to go to hit the ground on the spontaneous side. But if it's negative, it's going to tip the seesaw back the other way, away from spontaneous. Okay? But that depends on what enthalpy is doing, excuse me, on the left-hand side here. If enthalpy is negative, it's going to swing up that way towards the spontaneous side. And if it's positive, it's going to swing this seesaw back to the non-spontaneous side. It's going against that enthalpic drive. Okay, let's look at this possibility. A reaction that that releases energy, or is exothermic, or delta H is less than 0, is going to push up this side, okay? And also, it's saying its increases in entropy is going, so this side's going to push down on my seesaw. Well, if they're both kind of pushing in the same way, the left-hand side's pushing up, the right-hand side's pushing down, they're ensuring that my seesaw always lands on the spontaneous side. So, as we discovered earlier, and we talked about in an earlier question in the video, these two conditions help to push and to ensure that our reaction's always spontaneous. Okay, but let's look at the other combinations here. So a reaction that is endothermic, or enthalpy greater than 0, is going to push back down this way. Okay, it wants to go to the non-spontaneous side. And if the entropy is decreasing, going negative, it's also going to push up this side too and push it in the same direction. So those two conditions will always ensure that the seesaw lands on this side, or the reaction's always non-spontaneous. The reaction won't happen no matter if you put these materials together. Okay, not going to happen. But what about the other two cases? If you have positive enthalpy, okay, so going down this way, and positive entropy trying to push down this way, they're kind of pushing against the fulcrum. You don't know which side's got the largest push, okay? Will the entropic drive win, or will the enthalpic drive win? I mean, with that case, will the entropic drive win, okay? Will it be strong enough this side to ensure that it overcomes the push down that side, okay? Can we make delta S so big that it overcomes the enthalpy push back down, okay? And also, if you haven't... let's erase that first on my scribbles. Okay, the other situation, if we have negative enthalpy, or it's pushing up this way from this side, a negative entropy, that's good. I was missing some info there, okay? That's good. So if they're both pushing upwards, okay, it depends on which side is pushing upwards more to where it would hit. Okay, if the enthalpy is overcoming the entropy, it will slam back down and be on the spontaneous side. Okay, but on the other hand, if the negative entropy is so large there, it will push it over to the always non-spontaneous side. So for these two cases here, we don't know, we don't have enough information. We need to quantify which one is bigger to which way it'll push our little seesaw, okay, to determine whether it's going to be spontaneous. And our seesaw mathematically is this equation given here by some old guy named Gibbs. So lovely and respectful, aren't I? Josiah Willard Gibbs, apparently. I don't know much about him, but I love his equation, okay? It's a seesaw. And we'll start to talk about it now. So it's quantifying whether it will be spontaneous or not, okay? It also accounts for the difference of the temperature effect on entropy, okay? So here it is here. This change in energy, which is Gibbs free energy, okay, is a combination of the enthalpy and the entropy, but the entropy is multiplied by the temperature in Kelvin, okay, and there's a minus. So we're going to look at it's the enthalpy minus the temperature times the change in entropy, okay, and what it comes down to is, at this stage, we'll go in a bit more, but at this beginning stage, if the value that you get out of it, or the delta G, is less than 0, the reaction is spontaneous. It will happen. You put the stuff together, they'll react. And if delta J ends up being greater than 0 kilojoules per mole, the reaction is non-spontaneous. You put the two things together, they will not react. Okay? So we can calculate this. We've done that plenty of times using heat of formation values and stuff like that. And the question will probably give you the temperature. And we've learned in an early video for this chapter how to quantify entropy change. Okay? So one thing that I want you to note here is be careful of your units in your Gibbs free energy equation, because enthalpy is usually given in kilojoules per mole. And entropy is usually given in joules per mole per Kelvin, okay? So let's look what happens. Temperature will be given in Kelvin. So what you're going to get is Kelvin crossing out, and what you're going to have left is kilojoules per mole minus joules per mole. Don't make that mistake. Convert one over to suit the other. Now, the easiest way to convert these so that the units align is the enthalpy value from kilojoules to joules per mole. Okay, so change that to joules per mole. Or the other way that you can actually do it is to make this into kilojoules per mole by dividing it in by 1,000. Okay, but you have to align those two units. Let's see how we go. Let's see how my examples are. A reaction has a standard enthalpy change of delta S, the enthalpy delta H equals positive, I think I wanted 1200 kilojoules per mole. I think that's a typo on my part. Okay, at 298 Kelvin, temperature equals 298 Kelvin. The delta S, or the entropy for the same reaction, equals positive 8.90 joules per mole per Kelvin. What is the value for Gibbs free energy? Delta G equals question mark. Okay, in kilojoules per mole. All right. Notice they're both positive, so we've got one of those cases where the enthalpy is positive, so it's going against the enthalpic drive, but here we've got a positive entropy, so it's going with the entropic drive. So it depends on how the maths works out to whether it's going to go. You can't predict it here. So delta G equals delta H minus T times delta S. Okay. Now, look at my things here. Okay, what I'm going to do is, to align it, I'm going to put my kilojoules as joules per mole. Okay, so 1,200 kilojoules equals 1 200,000 joules per mole minus T, 298, times delta S, which is 8.90. Oh, I should have put my units for my Kelvin there so I can track it. Joules per mole Kelvin. Okay, let's check my units. Kelvin's going to cancel there, so I've got joules per mole going to joules per mole, so I'm going to get my answer in joules per mole. That's okay, I'll do that and then convert it over into kilojoules per mole. So I want 1,200,000. Have I calculated that correctly? Hopefully, minus 298 times 8.9. And I get an awful lot. I get positive 119374. Oh, 1197347.8 joules per mole, or divided by 1,000. Did I do this right? Yeah, I think it is. I'm just getting paranoid. 1,197 kilojoules per mole. Okay. I'm getting paranoid that that's wrong, but that's okay. It's got a very low entropy value. All right, let's do this one. Hydrogen cyanide. Please don't smell it. HCN, liquid, reacts with oxygen to form steam, carbon dioxide, and nitrogen gas. Give a balanced formula for the reaction. Okay, there's hydrogen cyanide there, HCN, liquid, reacts with oxygen, O2, to form steam, or H2O gas, plus carbon dioxide and nitrogen. Okay, let's make sure that we've got it balanced. Let's have a look. Where am I going to start? Okay, 2 nitrogens on the right, so I want 2 on the left. That increases my number of carbons to 2, so I'll put 2 molecules of carbon dioxide there. I've got 2 H's now, 2 H's, so that's all good. Now I need to balance my O's. I've got 4, 5 on the right, so I want 5 halves of O2. So let's go through and multiply everything by 2. Should I just change color and write it over the top? Okay, so 2 becomes 4. Sorry, that becomes 5. That becomes 2. That becomes 4. And that becomes 2. All right. Calculate the enthalpy change for this reaction given the heat of formation values in the table below. Okay, so my enthalpy equals the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. We did this last chapter. Go back and take a look if you're stuck. So our products are 2 water gases, and it's the enthalpy value here. So 2 times negative 242 plus 4 carbon dioxides. Carbon dioxide and the heat of formation value is negative 393. Was that 0.5? Yeah, 0.5. Plus 2 nitrogens. Oh, nitrogen, of course, is 0 because it's just nitrogen as it's found normally. Plus 0. Minus our reactants. So it's 4 times the hydrogen cyanide, 151.0, plus 5 times oxygen. Of course, oxygen heat of formation is 0. It's just oxygen by itself, how it's found in nature. Okay, put it in my calculator. 2 times negative 242 plus 4 times negative 393.5 minus 4 times 151 plus 5 times 0. Oh, that's the end then. Okay, negative 2,662 kilojoules per mole. So quite exothermic, that reaction, isn't it? A lot of energy left over. Okay, let's keep going. There's a part C and stuff over the page. Okay, so I'm just asking for the reaction again. I won't rewrite it. I'll just skip on up. Calculate the standard entropy. Oh, I might rewrite it actually. It'll help. 4HCN. Just bear with me. 502. What are we forming? 2 waters as a gas, 2 steams. How many 4 carbon dioxides? And how many nitrogens was it? 2. 2 nitrogens. Okay, this will help me in this standard entropy change, okay? So let's calculate our entropy change. The sum of the entropies of our products minus the sum of the entropies of our reactants. Okay, so 2 times the entropy of water as a gas. Water as a gas, that's 189.0. Plus 4 times carbon dioxide entropy, which is 214. Plus 2 times nitrogen. What was nitrogen here? 192. Okay, so there's my products minus my reactants is 4 times the hydrogen cyanide, 94.1, plus 5 times oxygen, which was 205.0. And that is joules per mole per Kelvin. Okay, 2 times 189 plus 4 times 214 plus 2 times 192. I'm going to just write my number down. 1618 minus, what is 4 times 94.1 plus 5 times, what is it, 205. 1401.4 joules per mole per Kelvin. So 1618 minus 1401.4, 216.6 joules per mole Kelvin. Could we have estimated that? Well, we could have, because look, liquid on the left, there's a gas on the left though, but all gases on the right, and an awful lot of them. How many? 8 molecules. Yep, that's pretty good. Although there's 9 molecules, but we've got liquid on the left, so liquid on the left loses the left out. So positive entropy. So this is an entropically driven reaction. And looking from the reaction below, it's also enthalpically driven. Okay, so the next question is probably going to be, is it spontaneous? You can go, well, without doing the numbers, they're both pointing in the same direction. But let's calculate Gibbs free energy at 45 degrees Celsius and comment on its spontaneity. So Gibbs free energy equals the change in enthalpy minus T times the change in entropy. What was our delta H? I'm going to do it this way, negative 2662. Negative 2662 kilojoules per mole minus T, 45 degrees Celsius, but 45 plus 273.1.15, 318.15 Kelvin, times it by, I'm going to do delta S in kilojoules per mole per Kelvin, so I'm going to divide it by 1,000, 0.2166 kilojoules per mole per Kelvin. Why not? I'm going to do it that way. Times 0.2166 kilojoules per mole per Kelvin. Now if I look at my units, I'm just going to make sure that they're going to cancel and be the same. Kelvin, Kelvin. So kilojoules per mole minusing away. I'm all happy with that. I can go ahead. So, negative 2662 minus 318.15 times 0.2166. Still a large negative value, which is good. 2730.911 kilojoules per mole. And our main thing that we're looking from, our Gibbs, is it is less than 0. So therefore, reaction is spontaneous. Maybe I should do another example here where I've got opposing drives. Anyway, that's a good enough example. Now you can do those and we'll talk a bit more about spontaneity.